Alright, so welcome back to your favorite inorganic teacher YouTube channel once again. Today is another episode. We want to look at how we can show or prove this particular work on the board right here. So we are to prove that this right here, x squared minus 1 yn plus 2, 2n plus 1 x yn plus 1, and then n squared minus m squared yn equals 0 right here. So what we are going to do is that we are going to either use this to prove this or we use this to prove that. So to be at the safer side, I think we should tackle this to prove this. Oh, what do you think? Well, let's go. Let's take this to prove this, right? So we are taking this indices to prove this right here. So let's go. Y power 1 over m plus y power 1 over negative 1 over m equals 2x. Now, this right here, we have to work it out. We have to change it, right? We have to change it. So we are going to have y power 1 over m plus y power 1 over m equals 2x, right? So this right here, we can decide to multiply through by y power 1 over m. So right here we have y power 1 over m times y power 1 over m plus 1 should be equal to 2x y power 1 over m, right? So when we do that, you know that indices said when they are multiplying and they have the same base, you add the exponent, right? So we're going to have 2 over m plus 1 should be equal to 2x y power 1 over m, right? So we know that this right here can be written as 1 over m all squared plus 1 should be equal to 2x y power 1 over m. So right here we can shift this here and then equate it to 0 so that we can have y power 1 over m all squared minus 2x y power 1 over m plus 1 should be equal to 0. So right here we are going to use the product. No, we are going to use the quadratic formula to solve this right here, right? So we are going to use the quadratic formula, right? So the quadratic formula says that minus b plus or minus square root of b squared minus 4ac all over 2a, right? And right here we can see that our a right from here is 1, our b is equal to minus 2x, and our c is equal to positive 1, right? So in doing, we are going to have y power 1 over m should be equal to minus is going to be 2x plus or minus square root of 4s squared minus 4 all over 2, right? So we have y power 1 over m should be equal to 2x plus or minus square root of, we can factor the 4 out, so we have 4 into s squared minus 1 all over 2, right? So this, we can say that we have y power 1 over m should be equal to 2x all over 2 plus or minus square root of, this will give us 2 right here all over 2, right? So we are going to have y power 1 over m should be equal to x plus or minus square root of s squared minus 1. So now what we have to do is that we have to differentiate, but before we can differentiate, we have to make sure that this exponent right here is just y. So we have to multiply each exponent by m. So we are going to have right here y power 1 over m should be equal to x. Because we are going to differentiate, let's consider only the positive aspect. So we have x into s squared minus 1 for m, right? So we can say that we have y is equal to s plus square root of s squared minus 1 for m, right? So this is what we have right now. So we have to take the first derivative, right? So when we do that, when we apply the differentiation on this, then we are going to have y prime, first derivative, right? Y prime should be equal to the differential of this right here. So we're going to use the power rule and then the chain rule together. So we drop this and then we are going to have m into x plus square root of s squared minus 1 or m minus 1. Then we differentiate the inner function, right? We differentiate the inner function, and that is 1 plus when you differentiate this, it means you are going to have 2x all over 2 square root of s squared minus 1. This right here. So this, we can say that we have y prime is equal to m into s plus square root of s squared minus 1 or m minus 1 into this takes this, and we have 1 plus x all over square root of s squared minus 1. This right here. So this can still break it down. So what we have to do right here is that we have to multiply through by square root of s squared minus 1. So when we do that, then we are going to have y1 or y prime into square root of s squared minus 1, and that is equal to m into s plus square root of s squared minus 1 or m minus 1 into square root of s squared minus 1 plus x. So this is what we have right here after multiplying through by the square root of s squared minus 1. So now let's proceed. Let's proceed from there. So let me clean this part. So let's go. So y prime into square root of s squared minus 1 is equal to m into x plus square root of s squared minus 1 or m minus 1 multiplied by x plus square root of s squared minus 1. Right, so this right here, we can break this down so that we can have something to substitute, because we have to substitute y which is right here into this. So we have to manipulate this to get y to substitute. So this right here, we can say that y prime into square root of s squared minus 1 is equal to, we know that m minus 1 is this. This right here we have here means that we have this right here minus 1, right? So we are going to have s plus square root of s squared minus 1 power m, right? Then minus 1 means that this right here was over over this whole thing, right? This right here means that m minus 1 means that this whole thing, this m minus 1 was over what? This same thing again, right? Multiplied by s plus square root of s squared minus 1 right here. So what we do next is that what can we do? Let me see on the track. Yep, we are on the way. So what we do next is that we have to consider this part. We have to treat this part very well, because you know that right. So we got a clue. So let's continue right from here. So we know that this m right here, this and this are having the same basis, so we add the exponent. So we have s plus square root of s squared minus 1. So we add the exponent, so we have m minus 1 here, and then this one is power 1, so it's going to be plus 1 right here. So we have this. Very simple. So you know this and this have the same basis, so we add the exponent, which is m minus 1 plus 1, and that is right here is equal to m into s plus square root of s squared minus 1. Now this takes this, and we have our m right here, and we can see that this right here is representing the y. It's representing the y, so we substitute this y here in place of this function. So we have y prime into s squared minus 1 is equal to m multiplied by y, because the whole function is y. So we do that substitution, then we can now differentiate the second time. So when we differentiate the second time, before we can differentiate the second time, note we have to square both sides. So squaring both sides, to avoid this square root here, we have y1 squared into s squared minus 1 should be equal to m squared y squared. Right, very simple. Calm down, just follow the procedure, and then you get it done. So right here now we can differentiate both sides. Right, very simple. So you know this is purely Leibniz theorem question, because you know Leibniz theorem, what he intends doing is that when you have two functions multiplying, that is the product rule, right? When the f of x and then g of x are multiplying, and then there are many, he intends to add them together, right? So this right here, you see, we have one function, another function, and then there is another function right here, right? So we have to use the product to differentiate them to the nth derivative, right? So right here, we are going to differentiate the second time. So when you differentiate this first term here, you are going to have 2y1 y2, right? Then we maintain this plus, we maintain the first term y1 squared into differential of s squared minus 1, and that is 2x right here. Then equals this right here. When we differentiate, m squared is 0, right? So we don't need to write it for the first term. Then we differentiate, we maintain the m squared, then we differentiate the y squared, which is going to be 2y1. So that is it. Now we move on. So we are going to have 2y1 y2 s squared minus 1 plus 2x y1 squared, and that should be equal to 2m squared y1, right? So what we have right here, we can now go ahead to divide through by 2y1, right? So we can divide through by 2y1, and then we have it done. So this right here, you can see that 2y1 is common here, 2y1 is common here, and 2y1 is common here as well. So what we do is that we divide through by 2y1, and that will give us the next result. So right, so y right here. So let's go to the next step. It's very simple. It's very simple. Right, so the next we're going to divide through by 2y1. So we have 2y1 y2 s squared minus 1, then plus 2xy1 squared. Then let's bring this right here so that we have minus 2m squared y1 y equals 0. Right, so right here we have this right here. So this is the second derivative. So what we do next is that we divide through by 2y1 because 2y1 is common to all the three terms. So we divide through by that, and we are going to have 2y1 here, 2y1 here, and then 2y1. So this takes off this, and we are going to have y2 into s squared minus 1 plus xy1 minus ym squared, and that should be equal to 0. Right, so this is what we have. This is the result after dividing through by 2y1. So what we do next is that we apply the Leibniz theorem. Right, so he says that if you have two functions multiplying and then one can be differentiated to a constant, the other cannot be differentiated to a constant, then you apply him. So we are going to use that theorem to arrive at this particular proof right here. So let's go. We have to consider this first, consider this, and consider this. So we have three terms that we have to consider in this particular function or this particular equation. So we consider this. Let's consider y2 into s squared minus 1. So when we do that, we consider this u as s squared minus 1 because that is the only function we can differentiate to a constant, right? So the first differential is going to be 2x. The second differential is going to be 2 right here. So we can identify our v now, and our v is equal to y2. So we can say that our Vn is equal to n plus 2, yn plus 2, right? Then let's consider the next one. So we consider xy1. So xy1 here, we say that our u is equal to x. So u1 is equal to 1. So we can say that our v is equal to y1, right? So vn is equal to yn plus 1, right? And then we can finally consider the last part, which is right here. So consider the last part, which is ym squared. Ym squared. So when we do that, then we say that our u is equal to m squared, right? So we can say that our u1 is equal to 0, right? Because m squared, m is a constant. So when we do that, we can say that u1 is equal to 0, and then we can say that our v is equal to y. So vn is equal to yn. So that is the parameters we have right here. So now we can go ahead and use the theorem, right? So clean this part, right? So now we can go ahead and use the theorem, which says that yn is equal to n combination 0 u vn plus n combination 1 u1 vn minus 1 plus n combination 2 u2 vn minus 2. It goes all to infinity, right? So now we are going to consider this theorem to plug in these parameters. So we are going to put these parameters into this, then simplify so that we can get our equation that they gave to us to prove, right? So here we are going to say that this right here is our first term, right? So this is our u right here. Our u here is s squared minus 1, right? And then our Vn is what? Our Vn is our Vn right here is yn plus 2. Our Vn is yn plus 2. Now, because we know that n combination 0 is 1, so we don't need to bring that part. Now, n combination 1 is n, right? So we consider the next part, which is this one, the 2, right? So we have 2x, then 2n, then we have vn minus 1, right? And that is going to be 2ns yn plus 1 plus n into n minus 1. You know, n combination 2, that is n into n minus 1, right? Then we have the next term following, which is the yn, right here, right? Plus x yn plus 1 plus n yn, and that should be, and then minus the m squared right here, right? So we have m squared yn, and that should be 0. So we simplify this, and we are going to have s squared minus 1 yn plus 2 plus 2nx yn plus 1 plus, when you expand this, you are going to have n squared minus n yn right here plus x yn plus 1 plus n yn minus m squared yn should be equal to 0. Now let's go up here. So when we go up there, we can say that x squared minus 1 yn plus 2 plus, you know, this and this are having common terms, so we factor 1 out. So this and this have, this and this rather have common terms, right? So we say 2n is 2n plus 1, so that we factor the x out, right? So we say that 2n plus 1, then we factor the x out, n plus 1, right? So you know this and this, I'm working on this and this, plus the next one is going to be this right here and this, because we have yn and yn, right? So when we factor the right, this right here and this right here, because we have n squared minus n, and then we have minus m squared, right? So we can say that we have n squared minus m squared yn, right here, and that should be equal to 0. Hence our formula is proven. Let's go back again. We see that this and this have some common items, because this, when we expand this, we are going to have n squared yn minus yn. So this will cancel one of this here, right? It will cancel that, right? So when we do that, that is what we are having here. So when we expand this, we are going to have n squared yn minus nyn. So this takes off this, so that goes off. So we consider this and this. And this and this, we can see that we have yn here, we have yn here. That's why the n squared minus m squared, then you factor the yn out. And that proves our formula right here. Right here. Ladies and gentlemen, this is so simple. We have been able to prove it. Just go through systematically. Follow steps by steps. Thank you very much for watching. Each time you press on my content to watch, I really appreciate you. Don't forget to press on the notification bell. I'll keep you updated on every concept in calculus and then in economics, especially economics for mathematics students. Thank you very much for watching. Bye.